Have you ever stopped to think about speed? I mean, really think about it. An explosion is over in a flash, right? But a piece of iron, it can take years and years to rust away. The world is just packed with chemical changes, but they all seem to be on their own unique clocks. So today, we're going to dive in and uncover the secrets of chemical speed. And to kick things off, check out this fascinating puzzle. Science, thermodynamics to be exact, tells us that diamonds, the hardest stuff we know, should naturally turn into graphite. Yeah, the same soft stuff that's in your pencil. But they don't. I mean, when was the last time you saw a diamond ring turn to dust? It seems to fly in the face of a basic rule of nature. So what's really going on here? Well, the whole secret lies in understanding that chemists are really asking two totally different questions. First, there's thermodynamics. That tells us if a reaction is even possible. Will it happen, yes or no? But then there's chemical kinetics, and that's our focus today. Kinetics asks a different question. How fast will it happen? You see, a reaction could be totally feasible, totally destined to happen, but it might take 10 billion years to actually finish. So, keeping that distinction in mind, let's start by digging a little deeper into this whole mystery. Let's explore the diamond's dilemma. And this isn't just about diamonds. It's everywhere. Think about dropping an antacid tablet in water. That fizz is done in seconds. Your food spoils over a few days. The paint on a car fades over years. The world is just a collection of countless reactions, and every single one is running at its own pace. So, to understand all these different speeds, we need a special kind of toolkit. And that toolkit has a name: chemical kinetics. It's the part of chemistry that is completely obsessed with reaction rates, the speed, and the step-by-step path, or what we call the mechanism, that a reaction takes from start to finish. Okay, so before we can even think about controlling speed, we have to be able to measure it, right? So how in the world do you put a speedometer on a chemical reaction? Well, the idea is actually pretty simple. Every reaction starts with its ingredients. We call those the reactants. And it ends with the results, the products. So we can figure out the speed by timing how quickly our ingredients are disappearing, or on the flip side, how quickly our final products are showing up. This graph shows it perfectly. Just look at this. The blue line, that's our reactants. It starts off high and then drops as the reactants get used up in the reaction. And the green line, that's our products. It does the complete opposite, starts at 0 and climbs higher and higher as more and more product gets made. The steepness of those lines at any given point literally tells us how fast things are going. Now, one way to talk about this speed is what we call the average rate. It's kind of like calculating your average speed on a long road trip. You take the total distance you drove and divide it by the total time it took. It's useful, it gives you the big picture, but it doesn't tell you how fast you are going at any one specific moment. For that, we need the instantaneous rate. This is the exact speed at a precise instant in time. It's just like glancing down at your car's speedometer. For us chemists, it's the slope of the curve on that graph at one single point. So, we can measure the speed. Awesome. But here's where it gets really fun. We can also control it. It's like chemists have these levers they can pull to make a reaction go faster or to slow it way, way down. Let's check out the most important ones. When it comes to controlling speed, there are three main levers we're going to focus on. First, the concentration of your ingredients. Second, the temperature. And third, the presence of something special called a catalyst. Now, theory is great, but seeing is believing, right? Let's look at a real experiment to see just how much concentration matters. We're going to watch the formation of a gas called nitrogen dioxide, or NO2. Okay, here's our starting line. In our first experiment, we set the concentration of both reactants to 0.30, and we see the initial rate of the reaction is 0.096. Got it? That's our baseline. All right, so here's the big question. What do you think is going to happen to the speed if we double the amount of just one of those ingredients, the NO, but we leave the other one, the O2, exactly the same? Take a second, make a guess. Whoa, look at that. We doubled the NO, and the rate shot up from 0.096 all the way to 0.384. Now, wait a minute. That's not double the speed. That's 4 times faster. This is incredible. It shows us that the rate isn't just a little bit dependent on concentration. It can be super, super sensitive to it. But why? Why does bumping up the concentration or the temperature have such a huge effect? To get that answer, we have to zoom way in. I mean, all the way down to the level of individual molecules and see what's actually happening. Here's the deal. For any reaction to even happen, the reactant molecules have to smash into each other with enough energy to get over a barrier. And this minimum energy needed, this hump they have to get over, has a name. It's called the activation energy. Think of it like an energy toll booth that molecules have to pay before they're allowed to become products. And this diagram right here is the perfect way to picture it. Just imagine your reactants are chilling at the bottom of a hill, and the products they want to become are way over on the other side. Well, to get there, they've got no choice but to climb all the way to the top of that hill. The height of that hill, that's the activation energy. If you can't make the climb, you can't have a reaction. Simple as that. So the big question is, how do we get more of our molecules over this energy hill? Well, we have two main strategies. On the left, you can see what happens when we raise the temperature. It's like giving all the molecules a running start. With that extra energy, way more of them are going to be able to make it to the top. But on the right, we see the other strategy, using a catalyst. A catalyst is like a secret weapon. It doesn't give the molecules a running start. Instead, it builds a secret tunnel right through the mountain. It creates a whole new path with a much, much lower hill, making the journey way easier for everyone. Okay, so we've learned how to measure speed. We know about the levers we can pull to control it, and we understand the energy hill that stands in the way. We now have every tool we need to finally crack our original case. So let's go all the way back to the beginning. Thermodynamics says diamonds should become graphite, but chemical kinetics shows us they pretty much don't. So what's the deal? And here it is, the answer. That activation energy, that big energy hill for turning a diamond into graphite, is absolutely enormous. It's not a hill. It's a Mount Everest of an energy barrier. At the normal temperatures and pressures we live in, basically zero carbon atoms have enough energy to even begin to make that climb. So yeah, the reaction is possible, but the rate is so ridiculously slow, it's practically zero. So there you have it. Kinetics is the hidden director behind the scenes, controlling the speed of everything from the flash of an explosion to the sparkle of a diamond that lasts a lifetime. Now that you know these secrets of speed, think about it for a minute. What's one change in your own life, maybe food going bad or paint drying, that you'd want to speed up or maybe slow down to a complete standstill?